Hello and welcome to Lecture 5, where we're going to discuss Section 3.3 from Survey 11th edition, covering the topic of relative velocity. All right, so this is a pretty concise lecture because it's just covering one topic, but it's a topic that really kind of needs its own attention. All right, just a few examples and let's get to it. Okay, so our objective is to apply the relationship between a particle's position, velocity, and acceleration as measured from two reference frames that move relatively to each other at a constant velocity and along a straight line. Okay, so we're not having there's no comparing between accelerating reference frames, at least not in any of the examples you'll see in this class. Okay, all right. Well, let's get to our key formulas. All right, so you can see there's three of them. They look quite similar. All right, what's going on? They're all vector equations. Well, the first one we just need to think about how to read it. So this is a velocity vector, and it's the velocity of A relative to B. All right, so it's A relative to B. All right, and I'll give you a concrete example in just a moment. And you would read this second term on the right-hand side as the velocity of A relative to C. And then, of course, this last one would just be the velocity of C relative to B. Now, the idea is that this is a true equation, that A relative to B is equal to the sum of A relative to C plus C relative to B. All right, why is that? Well, let's see. Right? So here's a picture. So the idea then is that VAB is playing the role of the resultant. It's this blue arrow here. All right, and then VCB is this one, and then the pink one is AC. Okay, and I changed the order then in terms of where as they're written in the equation with the tip to tail graphical representation, just as a good reminder that vectors obey the associative property, and it doesn't matter what order I add them in, I would get the same result, right? I'd just get a parallelogram if I did it in the other order, okay? Or together they'd all give me a parallelogram, all right? So what's going on then? This is just vector addition, right? Well, it is. It absolutely is. You can think of it as an application of vector addition. And all it's saying is that things can be moving relative to each other. That's it. It's relative velocity. Well, here's that concrete example I promised. So we could think of A as the ship. We could think of B as the coast, right? And then we could think of C as an ocean current. So then this first is then, let's read them out then. So the velocity CB would be the velocity of the ocean current relative to the coast. Okay, so that's just how the water is moving, all right? Okay, that makes sense. And then AC is the velocity of the ship relative to the coast. Relative to the ocean current, okay? So the ship is moving relative to still water, right? So it's moving relative to the water. Meanwhile, the water is moving relative to the shore. So then if we want to find the velocity of the ship relative to the coast, it's going to be the sum of the two. So one last time, the velocity of the ocean current relative to the coast plus the velocity of the ship relative to the ocean current gives us the velocity of the ship relative to the coast. Okay? Now, that's how you set up these problems. That is the idea. Okay? And of course, you could think of a boat or a ship that's moving against the ocean current exactly in the anti-parallel direction, so exactly at 180 degrees or against the current. And if it's moving at the same speed as the current, then how would the ship's motion look relative to the shore or coast? It'd be motionless, right? Because the ship would be trying to move one way, the current is meanwhile pulling it in an opposite direction but equal magnitude velocity. Yeah, it would be motionless relative to the coast, even though water would be rushing past it from the point of view of the people aboard the ship, right? The reference frame of the ship. So I think that's the idea. Is obviously it can matter, right? The idea of relative velocities makes a difference. Okay. Now the relative vectors can apply equally to displacement, and although we won't see examples of it, also acceleration. All right. So really what the equation we're primarily going to be using is the first one, the top one, the relative velocity equation, just like the title. All right, so I just kind of grouped the problems into two types because it was really kind of two obvious types. They're one-dimensional problems that have relative velocity and two-dimensional problems, okay? It occurred to me after the fact that the two-dimensional problems can be thought of as those where the vectors form right angles and those where the vectors don't form right angles because one is inherently more complex than the other. All right, but I'll kind of just call attention to that, but we'll think of it as one type of problem. Okay, so let's start off with a concept question, just a simple one to further illustrate the idea of relative velocities, and definitely try to answer it yourself before I go over the solution. Ryan, Samantha, and Tomas are driving cars at steady speeds. At the same instant, they each see a jet above with an instantaneous velocity of 200 meters per second and an acceleration of 5 meters per second squared relative to the ground. That acceleration will not come up in the question. All velocities are shown in the figure. Rank in order from smallest to largest the jet speed observed by each driver. Okay? Well, it's it. It's TSR, right? Just like the publishing company. All right? So how do we know that? Well, because we're asking for from smallest to largest, the velocity of the jet as observed by the drivers. Well, Tomas here is going to observe a jet that is only moving at 160 meters per second because he's obviously not catching up with the jet. The jet is getting ahead of him, but since he's moving pretty fast in the same direction as the jet, it doesn't appear to be moving as fast, right? That's kind of intuition. You should be able to think of that. A more concrete example, we could consider Ryan. We could set up the relative velocity equation with negative 200 for the velocity of Ryan relative to the ground, and then, negative 20, and then positive 200 for the velocity of the plane relative to the ground, then solve for the velocity of the plane relative to Ryan, and we get negative 220. So its speed is greater. The plane is moving away from Ryan faster than it's moving away from Tomas, okay? And its direction is different, okay, relative to the direction of Ryan. All right, so good kind of quick, rough idea about how we can deal with 1D. All right, in the next example, I'm going to kind of get a little bit into it more quantitatively, but it's still a simple question. So the police are chasing a bank robber. While driving at 50 meters per second, they fire a bullet at a tire of the robber's car. The police gun shoots the bullet at 300 meters per second relative to its barrel, which would also be relative to the police's car. What speed would an observer on the side of the road at rest measure for the bullet? So the idea is that police are moving at 50 meters per second, fire a bullet at 300 meters per second relative to them. Someone on the side of the road would observe what? Well, of course, 350, right? Because it would just be the speed of the car plus the speed of the bullet. So that person at rest on the side of the road would see that bullet fly by at 350 meters per second, okay? So that's the result we expect. Is that what we're going to get when we use the kind of more methodical approach of using the relative velocity equation? Well, it better be. So we'll define A for police, B for bullet, C for observer on the side of the road. All right, here I have a picture showing the two velocity vectors that we know already, and then we're solving for the third. All right, we want to find the VBC, the velocity of the bullet, relative to the side of the road. B for bullet, C for side of the road. All right, set up our velocity equation. Notice with the velocity equation that we confirmed a minute ago with our graph on the key terms that is consistent with tip to tail addition. What we see here, right, that it's that AB on one side, and then on the right hand side it's AC, CB. I bring that up because I always think of C as being sandwiched in, because the idea is then when you add these two vectors together, the C essentially disappears and you're just left with the outside of the subscripts AB, which agrees on both sides. Okay. So, but let's think about what we actually know and what we want to find, all right? So I'm going to reorient some of these vectors, all right? In other words, I'm going to multiply some of the vectors by -1, thus changing them or rotating them by 180 degrees. Because if this is VAB, then this is VBA. Thus, when I multiply a vector by -1, I swap its direction. And for relative velocity, that means swapping the subscript, all right? Because if something's moving to the left relative to me, relative to that object, I'm moving to the right, right? Does that make sense? I mean, think about, in a train, like it's, you're the moving one, but if you were to suspend disbelief and think that you were at rest, then the ground would appear to be racing backwards, okay? So that's why if I want to reorient the subscript AB to BA, I have to pick up a negative in front. All right? Now, why would I want to do that? Well, because I know BA. I know the velocity of the bullet relative to the police. Now, you might say, well, why didn't I just choose different subscripts? Why didn't I, choose A for bullet and B for police, and I wouldn't have to switch them? Well, because I want to make the point that you can choose any letter you want for A, B, and C. or you can choose, you can match any object with any letter, I should say, right? So I can define A as the side of the road, I could define it as a police as I did. It doesn't matter, you'll always be able to solve the problem, okay? All right, so VAC we can just leave as is, because that's the velocity of the police relative to the side of the road, which we know. And then we're trying to solve for the velocity of the bullet relative to the side of the road, but as written, it's the velocity of the side of the road relative to the bullet, so we need to swap this one as well 180 degrees, thus picking up a negative. All right, so then I'm going to go ahead and solve for the velocity I'm interested in, the velocity of the bullet relative to the side of the road, and I find that it's just the sum of the two, but of course it is. And when I plug in the numbers, I get 50 plus 300, or 350 meters per second. Okay, so good, our intuition was correct, or maybe it's more like the equation works, right? All right, so now let's do it for a slightly more complicated case. Part B, if the robber's car is moving at 65 meters per second relative to the observer on the side of the road, how fast is the robber's car moving relative to the bullet? All right, so let's see. So now, and this is interesting because we're not asking for how fast the bullet is moving relative to the robber's car. We're actually asking for how fast the robber's car is moving relative to the bullet. So now we're as if we're on the bullet, or the bullet has some consciousness, and it's saying, oh, look at that robber's car. It's, you know, moving in a certain way. You know, maybe I'm at rest, right? So part B. Here's the picture. There's two cars now. All right, here's the velocity of the bullet relative to, well, let's give our letters, relative to the police, okay? And here are two velocities. This would be the velocity of the police relative to the side of the road, and then this one would also be the velocity of, well, in that case, the robber relative to the side of the road. But notice the side of the road doesn't show up as one of our subscripts. That's because I'm going to skip a step, because technically we would have had to figure out what the velocity of the robber's car is relative to the police car by comparing them both to the side of the road. So essentially do what we did in part A again. But since I feel like that is fairly intuitive, I'm just going to skip that step and say that we already know that the velocity of the robber's car, C, relative to the police is 15, okay? And that's because the robber's going 15 meters per second faster than the cop, right? 50 for the police, 65 for the robber. That means that the robber is gaining ground on the cop at a rate of 15 meters per second. Okay, it's just the difference between them, okay? But let's go ahead then and set it up and solve for the velocity of the robber's car relative to the bullet. All right, do I have to change some subscripts? Yes, indeed I do, all right? So I have, because I'm just interested in the ones that I already know or seek to know. All right, so now I have the velocity of the bullet relative to the police, which I know, all right, with a negative in front. The velocity of the robber relative to the police, which we figured out we knew. And then the thing I'm looking for, the velocity of the robber relative to the bullet. So that's the only one I left and didn't switch the direction or the order of the subscripts, all right? All right, and then I go ahead and solve for that one unknown, the velocity of the robber relative to the bullet, all right? All right, and then I get, oh, and this should be, I do have a small typo here, you may have noticed. Right, of course, I'm solving for the velocity of the robber relative to the bullet, which is what, indeed, all I've done here from this line here to this one is just add VCA to both sides, which is why it became positive, and the negative VBA remained on one side as negative. But notice I accidentally wrote it as BC, not CB. So this should be CB, like that. All right, that's a typo. All right, and then it's 15 minus 300, which gives us negative 285. All right. So from the point of view of the bullet, the robber is moving backwards at 285 meters per second, because it would appear to the bullet that the robber is flying towards them, right? And towards them would be the negative x direction, thus backwards, thus negative. Okay, good, right? Definitely thoroughly explained that. And again, it's kind of something you could have figured out, but we're really showing how to do it in the slow, assured way of using the relative velocity equation. All right, now let's really make it matter with some 2D examples. All right, so first a concept question. Two projectiles are in flight at the same time. What is the acceleration of one relative to the other? Think about it for a minute, but you know the answer. 0, since they are both accelerating at the same rate, right? So even though, you know, one of them may have been dropped sooner, you know, one may have an initial velocity and the other doesn't, relative to each other in terms of acceleration, none. Since they're both accelerating at the same rate, okay? All right, so example 2, our first 2D problem. All right, and this is one where the two velocities, so the two velocities that are known, which is going to be the velocity of the stream and the velocity of the boat, they're perpendicular to each other. So right away we have basically a right triangle to set things up. And so that's what I mean is in terms of type 2 problems, of 2D problems that involve relative velocity, the ones where the two given velocities are perpendicular are the easier type. Okay, in example 3 and example 4, I'll do problems where the two given velocities are not perpendicular to each other. All right, so anyway, a motorboat is crossing a stream that is 112 meters wide. The stream has a flow rate velocity of 1.22 meters per second to the east as shown. The boat starts at point A and heads towards the north with a velocity of 1.88 meters per second, so faster than the river, okay, in a different direction. And that velocity is relative to the water, okay? How far does the stream, down the stream, point C, does the boat arrive when it has crossed the stream? Because it's going to get pulled downstream, right? It's trying to head straight to B, naively, but of course that's not going to happen because it's going to get pulled downstream as it crosses, okay? But its heading is pointing straight to B the whole time, or at least straight across the whole time. What must be the angle of the boat relative to north if it wishes to arrive at point B directly across the stream? That will be part B. All right, so I've drawn a couple things. We actually aren't going to need this picture until we get to part B. Here I've just defined that I'm calling the width of the stream y, and I'm calling the streamwise drift of the boat x. All right, here I've just drawn the vectors showing that the two velocities that were given, the boat relative to the water and the water relative to the shore, are at right angles to each other. Okay, and essentially, this is the east direction and this is the north direction. All right, and in fact, that's exactly what they are. All right, this is a velocity of the boat relative to the shore, bs. All right, v sub bs. And we don't know that, okay? We actually don't need it right away, or really, we don't need it explicitly, although you could use it to solve the problem. And also, what I've done here differently, just to show we can, is we don't have to stick with the whole A, B, C subscripts and assign those to different things. Instead, we could use whatever letter we want, and perhaps we can use letters that make sense, right? So B for boat, W for water, and S for shore, okay? All right, but notice that the subscripts still work out. If we think about this, I'll show you. VBS, or V sub BS, equals V sub BY plus V sub WS. And sub just means subscript, of course. Right? The W is sandwiched in there. The outside subscripts WS or BS match up on both sides. Okay? All right, and then what we're going to do is we're going to consider the boat relative to the water, which we know to be 1.88 meters per second, and set that equal to distance over time, all right, because it's constant velocity. All right, and then to solve for the time to cross the stream. So 112 meters divided by 1.88 meters per second gives us our 59.6 seconds. All right, that's how long it takes to cross. Well, in that time, the stream is pulling the boat to the east. So we just take the velocity of the water relative to the shore times the time that we solved, 4, and we end up with 1.22 meters per second times 59.6 seconds, and that gives us 72.7 meters. All right, so it gets pulled quite a bit downstream, right? Okay, so in part B, we don't want to get pulled downstream. We want to actually arrive at B. So now we're going to angle our velocity of our boat relative to water vector. Okay, the one I've drawn here. We're going to angle it upstream a certain angle theta, and we want to solve for that angle. All right, that is what we're solving for. Okay, so how do we go about doing that? Well, we consider components. So I'm going to consider the streamwise component FBWX. All right, and in magnitude, that component of the boat relative to the water velocity has to be equal to the streamwise direction of the water relative to the shore. Well, of course, VWSX, all right? Well, that's just the full WS, right? Because of course the water is entirely flowing in one direction, okay? In the X direction. Okay, so then it just becomes this, FBW sine theta, y sine theta, because it is this side of the triangle, so it's the opposite relative to the angle that we're looking at, right? Okay. And so then it's just a matter of isolating theta, taking inverse sine, plugging in my values. So it's just going to be inverse sine of the water velocity divided by the boat velocity. And we get 40.5 degrees, all right? There you have it, right? That's the rate at which, or that's the angle that the boat would have to turn at to actually, get across, okay? And not drift. All right, hopefully that makes sense. And as I mentioned, that this problem is all about right triangles, right? It's very much like just a trig problem. You can almost just solve it purely as a trig problem without even really thinking of it as relative velocity, okay? But now we're going to see our final two problems where it really, really is going to benefit us to go through that process of setting up the relative velocity equation and thinking about it very thoroughly. All right, so first one, the simpler of the last two. All right, so in the figure, a plane moves due east while the pilot points the plane somewhat south of east towards a steady wind that blows to the northeast. Okay, so you see everything's kind of not at right angles to each other. The plane has a velocity defined as PW, all right, so that's plane relative to wind, with an airspeed, so that's the speed relative to the wind, of 250 kilometers per hour. We're going to convert that to meters per second. Directed at an angle theta south of east. The wind has a velocity of wind relative to ground, all right, of 65 kilometers per hour, which is directed 20 degrees east of north. So first of all, what is theta? And then what is the magnitude of the velocity of the plane relative to the ground, all right? So let's take a close look at the picture here. So the idea is we have the plane, right? Here's the theta we're looking to solve for. Essentially, this is the heading that the plane needs. Because the way I think of this problem is very similar to part B of the boat crossing the stream problem above. This plane wants to make sure that it's heading due east, okay? Which is probably something planes want to do. But in order to do that, they have to account for the wind. And they know that the wind is blowing, well, east of north, okay? They know the velocity of the wind and its angle, specifically 20 degrees east of north, okay? So that means that in order to make sure their heading remains due east, they need to kind of fly into the wind a little bit, okay? Because otherwise they're just going to get pushed off track, okay? So they fly into the wind, all right, at a heading that is a certain amount south of east, all right? As you can see, the theta is south of east. In doing so, their actual direction, the velocity of the plane relative to the ground, will be the desired direction of due east, okay? So then, as we think about that, this is the triangle that we get. This triangle is not a right triangle. It's two separate right triangles. See that? All right. So there's an extra step there. We have to think of our triangle, yes, right, which is just a tip-to-tail velocity addition problem, which is just a relative velocity problem. But we have to think of that triangle as two separate triangles, which means take components. And that's it. Okay, that's the procedure. Okay? All right, so let's see what that actually looks like. So first of all, we write out the relative velocity equation. The velocity of the plane relative to the ground is equal to the velocity of the plane relative to the wind plus the velocity of the wind relative to the ground. All right, and then we split it into components. We look at this, because this is a vector equation, right? And so we can't do anything with it algebraically. But if we split it into two separate component equations, then we can do a lot with it, all right? And what does it look like as two separate component equations? Well, there's the x component, all right? So we're going to have the speed of the plane. Oh, and I did misspeak a minute ago. In this problem, we don't have to convert to meters per second. In this particular one, we can leave everything as kilometers per hour. Because, it's basically, we're just asked for the angle and then the magnitude of the velocity, but we might as well leave it in the units given. All right, anyway, so we have 215 times cosine theta. That's the x component. Cosine, because it's the adjacent side. All right, plus 65 times sine of 20. Sine for the x component of the wind, because 20 is measured relative to north, whereas theta is measured relative to east. See? All right. And then we move on and we say, okay, well then theta is this way. Theta is actually measured in sort of the clockwise direction, right? So not the typical direction like the unit circle, which means that the horizontal component is actually negative, all right? And you can just ascertain that by just looking at the fact that it's angled downwards, okay? And I'm calling north y, so north is defined as y, and east is defined as x, if that's not obvious, okay? And then for the wind, it's just 65 times cosine, because it is up, right? It's in the north direction, and it's the adjacent side of the wind right triangle. All right? So then it's just a matter of solving for theta. It's as simple as that, right? So we can use either one of these equations to solve for theta. I'm going to use the VPGY equation. Just isolate theta with inverse sine and moving everything to one side, and we get 16.5 degrees. We now know theta, all right? So the heading of the plane has to be 16.5. But that's not all. If the plane just changed its heading and sort of headed to the south of east at 16.5, that wouldn't be enough. It would still get blown off course. It has to adjust its speed as well, all right? Or maybe a better way to think about it is I actually misspoke there. It's not the plane adjusting the speed. I keep thinking of different problems. It's the fact that relative to the ground, the plane is going to have a different speed than it's measuring relative to the air. because planes actually do measure their speed relative to the air. They can do it with these pressure gauges. And so the plane would be measuring a certain speed relative to the air, but if they wanted to know how much ground they were covering underneath them, it's going to be a different number. And it's going to be the number we get by solving part B of this problem. Okay, so let's go ahead and do it. So we want to find that the x component of the plane relative to the ground is equal to the velocity of the plane relative to the ground. Okay, so basically what I'm saying there is I'm just taking the two components. Excuse me. So the plane relative to the ground is entirely in the x direction. That's why I can just drop this subscript, because essentially it's moving due east, which we call x, and so the entire velocity vector is in that direction. Okay, and so then all I want to do is just add up the x components of the two vectors, tip to tail addition, that gave me VPG, right? Which would just be the horizontal component of that vector, and then the horizontal component of the wind vector. Okay, so horizontal component of the plane vector, horizontal component of the wind vector. All right, at least the plane relative to the air vector. All right, so that's all I do here. And again, we already discussed why one is cosine and the other is sine. Add them together, right? Now that we know that 16.5, see how we needed 16.5 to solve this? All right, and we get 228. Okay, so because the wind is a tailwind, it actually speeds up the plane once the plane adjusts for the fact that it wants to keep a due east heading. The plane is going faster relative to the ground with that tailwind than it would be otherwise. Now, is the wind entirely a tailwind? No, obviously not. Only one component of the wind, the east component of the wind, is the tailwind. Okay, all right, let's do it one more time. Okay, so a plane with a speed relative to still air is 51.4 meters per second, all right? And it's heading due north. After 1 hour, an observer on the ground below sees the plane has only traveled 135 kilometers, all right? And that the plane is 15 degrees to the east of a direct path north. So unlike the previous problem where we were assuming the pilot knew what they were doing and they adjusted their heading so that their velocity relative to the ground would be in a cardinal direction, here we have a plane that is just trying to just go in a certain direction, not realizing that they're getting blown off course. And there's just someone on the ground being like, hey, this isn't working. Okay, so let's draw the picture first of all. We're just going to draw the vectors of the plane relative to the air, the plane relative to the ground, and the air relative to the ground. All right, so here's our vector. All right, P for plane, A for air, G for ground. All right, now you can see there's a bit going on. Again, it's not a right triangle. So the idea is that we have the velocity of the plane relative to the ground is the sum of the two vectors. Okay, so it's the sum of the blue vector plus the pink vector. Okay, in other words, blue vector plus pink vector gives me dark orange vector. All right, so here's the tip to tail. This one plus that one gives me this one. And this might throw people off because the vector that's the sum of the first two, the velocity of the plane relative to the ground, is actually shorter than the velocity of the plane relative to the air. That's because in this problem, one component of the wind, specifically the vertical component, so the air relative to the ground in the y direction, this vertical component of the wind, it's not a tailwind, it's a headwind. So it's actually slowing the plane down, which is why the observer on the ground saw that the plane had only traveled 135 kilometers. Because they haven't done the conversion yet, but it turns out that moving at 51.4 meters per second means you should go further than 135 kilometers per hour, okay? All right, but relative velocity means you're not. So first of all, let's define our variables. I think I already did that pretty clearly, all right? And then to find the speed of the plane relative to the ground in meters per second, left off my unit there, we just take the 135 kilometers, which is 135,000 meters, and divide it by the number of seconds in an hour, which is 3,600. So then you find out that the magnitude of the velocity of the plane relative to the ground is only 37.4 meters per second, significantly slower because of that headwind. Okay? All right, so in other words, the magnitude of this dark orange vector is that much shorter than the magnitude of the blue vector. All right? And by the relative velocity equation, we just write it out as a vector equation initially with all the subscripts we discussed, okay, that match up with the picture. Then we split it into components. By the way, I'm just clearly showing that air relative to the ground is just another word for wind. Okay? And so split the vector relative velocity equation into components, because that's the only way we can solve it. Okay? So just like in the previous example, that's what I do. Okay, then I'm going to then solve for my two unknowns. All right, my two unknowns, there's one per equation, is just the x component of the wind and the y component of the wind. All right, that's it. I know everything else, right? I I know everything about the velocity of the plane relative to the ground, and I know everything about the velocity of the plane relative there, but I don't know anything about the wind. So now what I find is that the wind has a x, or east component, of 9.71, and it has a y, or south component, of 15.2. Why south? Because it's negative, it's pointing down, and up is defined as north. All right, so the magnitude of the wind is, using the Pythagorean theorem, right? Because of course, this is a right triangle, right? And I clearly show the two right triangles, the pink and the dark orange one, that form the non-right triangle that's composed of all three vectors. But anyway, so when I take my two components of the velocity of the wind, square them, put them inside the square root, square them, sum them, take the square root, and I get 18 meters per second. Okay, so that's the length of the pink vector. All right? And to find the angle theta, and theta here is just the velocity of the wind. I've defined the velocity of the wind relative to due east, all right? And I say, what is the angle of the wind velocity relative to due east? Okay, I wasn't sure if I had specified, I couldn't remember, yep. So this is it specified relative to due east, okay? And we go through there. I'm gonna use tangent inverse of v of the vertical component of the wind divided by the horizontal component. Why can I do that? Well, because this angle here equals this angle, and so then opposite over adjacent is vertical over horizontal, or north over east. All right, so plug in my numbers, 15.2 and 9.71, which I know from here, okay? And then I get a magnitude angle of 57.4 degrees, all right? And I know that that angle, based on my figure, is south of east. Now I could have defined it, the unit circle way, instead of the counterclockwise direction, I could have defined it as north, right? And it would just be 360 minus this. But I think this way is more clear, especially since I specify the direction, okay? All right, well that's it. That's our final example, all right? So hopefully you really kind of see what relative velocity is like, and how it really is just an application of tip-to-tail vector addition and splitting those vectors into components if necessary. Thank you so much for watching, and please send me any questions throughout the week on this material. Bye.